In this video, we're going to be talking about the rate law equation. Yeah, so before we continue, if you haven't seen our introductory video on rate, that's kinetics, you can go to our playlist and check it out. Alright, so today we are talking about the rate law equation. The rate law equation. Now we have to know that any chemical reaction has a relation on which the rate of the reaction depends, and that brings to what we are talking about today, which is our rate law equation. This can also be simply referred to as the rate equation. Rate equation. Rate equation. Alright. Now, in any chemical reaction, we have series of reactions that takes place before we have our final product. Now, among this series of reaction, there is this one reaction which is referred to as the rate determining step. Rate determining step. In short, you can call it the RDS. Now, this RDS is the slowest among all the series of reactions that complete the main reaction. So, let's say we have this reaction over here. Let's say we have B plus with a catalyst. Let me look here. With a catalyst X, and then we are getting B A subscript 2 as our product. So remember that our X over there, our X is the catalyst. Our X is the catalyst. Alright, so how do we get this product? How do we get our product to be BA2? What actually happens is there are a series of reactions that actually takes place to give us this main product. So let's look at what happened. Now we can see that the reactions proceed by these steps. Maybe firstly we might have our molecule A dissociating to give us 2 moles of A, which is going to be really fast reaction actually, and then we'll have the dissociation or the association of B with A. And then our catalyst X. Remember, it's just there to speed up the reaction. So we have this combining, and it's giving us our BA and then we have our catalyst still in the solution, so let's put there our X. Alright, this is also going to be really fast. It's going to be a fast reaction. Now we'll have the final reaction, which is going to be, let's call it number 3. Our final reaction, which is going to be B plus molecule A to give us our final product, which is going to be and then we have a molecule A again, so we have A, and this reaction is really going to be very slow. is going to be slow. Alright, so these three series of reaction, we look to find out that the slowest among them is what? The reaction step 3. The reaction step 3. So this reaction step 3 is what we are going to refer to as what? Our rate determining step. Our rate determining step. So our RDS is going to be equal to step 3 or reaction step 3. Alright, we will deduce our rate equation from the reaction step 3. So for, let's say, any given reaction in the form this, let me use this, any given reaction with the form x a plus let's say y b, then we are going to have our products, and we have our products, PDT for our product. Alright, and assuming this reaction is the rate determining step in whatever reaction steps we are looking at, then we'll say that the rate law equation of this RDS is going to be given by the relation R K and we'll bring our x, then we have our b raised to the power y. Alright, so this is what we refer to as a rate law equation. So over here we'll say that our R is going to be so let's see where R is our rate of the reaction, okay, and K over there is a constant and it's known as the specific rate constant. The specific rate constant. Alright, let's look at R. So now rate is defined as the change in concentration of a reactant per unit time. So let's say let's underline this, change in concentration of reactants per unit time, or change in product per unit time. So how do we express this mathematically? If we have our rate R, this will be equal to the change in reactants, so that will be D, difference in reactants, with respect to the change in time. So the reactants over dt, that is what the mathematical expression for rates. And then it also mentioned that all the change in products per unit time. So this same R can be expressed as being equal to positive. Alright, over here it's going to be negative. It's going to be negative because the reactants are being consumed in the reaction. They are being consumed. So in a case where we are looking at the products, because products are being formed over time, so we are going to say that it's going to be the change in the products. So let's say over the change in time. So this is the expression for rate. Remember, if it is the reactant, is going to be negative, but if it is a product, it's going to be positive. So when we look at concentration is given by what? Mole per dm cube. Mole per dm cube. And then we have our time being in hot seconds. So if we rewrite this in applying indices and applying the laws of indices, then it's going to give us mole dm cube per seconds. So basically that is the unit for it. That is the unit for it. That is mole per dm cube per seconds. All right. So now rate constant is the constant of proportionality in any rate law equation. It's a constant of proportionality. In other words, it is that rate when the initial concentration of all the reactants are 1, of all the reactants being 1. So once we have to know that this k, which is a constant, is it is constant anyway, but it varies with what temperature. It varies with temperature. So when temperature is constant, then we can say that our k will be constant. But when temperature changes, then it also changes. So it varies with changing temperature. All right. Now when we go back to our rate law equation, we find out that R is equal to K, and then we have the concentration raised to the respective orders. Alright, so if we want to find K from this equation, what do? We have to divide through by the concentrations. So we'll put right here, we have our A to the power X. Then we have our B to the power Y. And we divide this side too with the same thing. So we have our A to the power X, and then we have our B to the power Y. So what will happen in this, will cancel this out. So our constant is going to be equal to the rate divided by A this to the X and this to the Y. Alright, so looking at this, we can say that K has no definite unit. It has no unit, because when we look at this, we'll see that R is measured in mole per dm cube per hot seconds per seconds. It's been divided through by what these concentrations raised to their respective powers. So if we take A, its concentration is going to be mole per dm cube, and remember it's raised to the power X, so let's put that in bracket here and bring our X. And the same thing is going to be for B, also as the unit mole per dm cube. Put this into brackets and we have our Y over here. Alright, so if we integrate this, then if we go through with this, then we're going to have, what is going to happen is that we'll have our mole per dm cube per seconds, and then when we come down here and applying this is going to give us mole, sorry about that. Alright, so we now have K with the unit mole. It's going to be 1 minus X plus Y per seconds. So you find out that it has no definite unit, but it's dependent on the X and the Y. Okay, the X is referred to as the order of the reaction with respect to A. The order of the reaction with respect to A. And then the Y is the order of the reaction with respect to B. So this is A. And Y is the order of the reaction with respect to B. So now when we add up x and y, it will give us what we call the overall order of the reaction. Okay, so looking at how we can apply this, assuming you have this equation which is a plus 4b giving us 3c plus 2d, how would you write the rate equation of this reaction? So it is very simple. You write your r, what is going to be equal to, remember to bring your constant, and then you bring the concentration. Anytime you write this in a square bracket, it means it's talking about concentration. So what is the order of A? That is the mole of A, the mole attached to A, and then we say that is what 1. So over here is 1. Because it's 1, we are not going to write anything there. So let's bring our B. What is the order of B? It is what 4. So we'll bring in our 4. It is that simple. So that is the rate law equation for this particular reaction. Alright, so having this in mind, then we can write the rate, we can express the rate mathematically with respect to the reactants and the products. So when we take the reactants, this is going to give us R. Remember, it's negative when we are dealing with reactants. So R, then we have the difference of A with respect to time. So let's say dt. Okay. Alright, what about taking B? What if we take B? Then our rate is going to be equal to 1 out of 4. 1 over 4. Remember, the mole of B is 4. And then it's also going to be negative. So we have our TB in our square brackets with respect to the change in time. That is going to be the rate, the mathematical expression for it. When you go to the products, remember over there in the products we have C, and then we have D. So it is going to be the same process, but remember when I write in the mathematical expression for products, it's going to be positive. Alright, if you like this video, remember to give a thumbs up and hit the subscribe button, and then watch out for the next tutorial on rates of reaction.